Resistance, okay, resistors in series and in parallel. So this is lesson 9, okay, and also look at how to measure resistance using obviously an ohm meter, which we've been doing all the time, but we also are able to measure resistance using a wonderful device called a meter bridge, which we'll look at. Okay, so first of all, resistors in series. Okay, now you expect that if you have two resistors in series, okay, so we call them R1 and R2. And we say the EMF, so the total voltage of circuit, is E. So that would be the power supply, let's say 6-volt battery. Okay. You'd expect, as you put in a resistor, another resistor after the first resistor, you expect the total resistance to go up, and it does. So we derive a formula for this. So let's look what we do. Okay. So basically, we know already what the idea. This is effectively a potential divider. So we know that the EMF, so the energy supplied per coulomb, which is this, is used to get the charges through R1 and the charges through R2. So the energy required to get it across R1 is called V1, which we could measure with a voltmeter, and across R2 we call it V2. Now we know from common sense that E is equal to V1 plus V2. We have E volts of energy available and we need to use it in two places. So we use it in V1 and V2. So the E volts is equal to V1 plus V2. Remember, we also indicated there is an internal resistance in the power supply, which we ignore. Okay, so E is V1 plus V2. That's also known as Kirchhoff's law, Kirchhoff's first law. Kirchhoff has two laws. He's not explicitly mentioned in the course, but we use him. Okay, first law, total EMF for the circuit is equal to the sum of all the potential differences of the circuit. It's kind of obvious, but we'll go with it. Okay, right. So we have this. Okay, and now we're going to apply Ohm's law to all of these. Okay, so for Ohm's law, we have the total EMF of the circuit. So we know that Ohm's law basically is V is equal to IR. So in this case, it's going to be the total current in the circuit, which we're going to call R, by the total resistance in the circuit, we're going to call RT. Now, if you watch it here, the current flows down here, and there's nowhere for the current. Current is only one path all the way around. So the total current is the same all the way through the circuit. I could put the ammeter there, or there, or there, and I'll get the same value. Okay, the current is constant throughout the circuit because there's only one pass. Has to be, right? Now, for voltage across 1, we're interested in Ohm's law just for this bit. So it's the current going through it, which is again I, by the resistance in that area, R1. So we're only talking about this area here. So the current is still I, and the resistance in that area is R1. And in the same way, current going through here is I, and the resistance is R2. Okay, so in each case I've applied Ohm's law to the whole circuit here, and I've applied Ohm's law to part of the circuit in both of those. But you can see that if we divide across now by I, okay, divide across by I, we end up with RT is R1 plus R2. And that's what we expected. Okay, you use that in junior cert. Okay, so if I have a 3 ohm resistor and 6 ohm resistor in series, in other words, one after the other, it's effectively the same as a 9 ohm resistor. Fine. Okay, boring stuff. Okay, but now comes the exciting bit. Okay, resistance in parallel, where it doesn't do what you'd expect it to do. Okay, so let's have a look. Right side, just let it clean that. Okay, so right, so resistors in parallel now, and this is the one that is rather interesting and a bit counterintuitive. Okay, you wouldn't expect it to happen, but it'll all make sense, and it's linked to resistivity. We'll have a link between the two of them as well as we go on. Okay, so we're interested in resistors in parallel. So we have our EMF, and this time we put two resistors in parallel, so like that. That's what we mean by in parallel. Okay, R1 and R2. Now let's have a look at it. We have a current coming down here, and this time we're going to call it the total current. Because when it comes in here, some of the charge is going to go up, some is going to go down. So I'm going to call that I1 and that I2. And we're going to be using another Kirchhoff's laws. Now in a second, okay, another Koppen law, right? And we've R1 and R2. Now the voltage, okay, across here, if you think about it, if you put a voltmeter between here and here, same as putting a voltmeter between here and here, so the voltage across on R1 and R2 is the same because they're in parallel. Okay, so all we can do is find the energy needed to bring the charge from here to here. And in fact, if you think about it, that is the EMF of the circuit, because that's the only place it's using energy. So E will be equal in here, E is equal to V in this case, because there is only one V down here. So this time, instead of starting with the V's, we start with the I's, because the I's split. So the total current, according to another one of Kirchhoff's laws, is I1 plus I2. Does that make sense? Current in is IT, current out must be the same. So the current in into this spot here is IT. Current out is I1 plus I2. Current doesn't disappear, the charge doesn't disappear. Okay, so it is equal, they're equal. Right, okay. We're now going to apply Ohm's law again, and this time we're applying Ohm's law. Okay, obviously we're going to use in the version I is equal to V over R. Okay, we're going to use V over R. So let's go through it. Total current is E, the total EMF in the circuit, over the total resistance. V1 over R, V over R1, there's only one V for that one, and for this one, the voltage is V, plus, and resistance R2. Okay, but E is equal to V. Okay, we know that. So if we can be posh about it, take out the E here, take out the V here, cancel because they're equal. You could just cancel them at an earlier line, and we end up with this. That all looks very innocent. Okay, and that's our formula. 1 over RT is equal to 1 over R1 plus 1 over R2. But tomorrow lesson, we'll see there's something bizarre going on here, because what happens when you put them in parallel is if you put a resistor, let's say of 10 ohms, into a circuit in parallel to another resistor, you reduce the resistance of the circuit. You put in a resistor, but you reduce the resistance of the circuit. Tune in tomorrow, okay, to figure that one out, right? Okay, so that's that, right? Okay, so there are first two proofs, and there are only two proofs that we have to be able to do. Okay, third thing we want to look at in this class is the Wheatstone bridge, okay, and the meter bridge. Okay, so the meter bridge is a special setup where you put two resistors in series and another two resistors in series. You may well ask, why am I putting them in diamond shape? Because that's traditionally the way it's done. Okay, look in a sec. Back around to here, and between here and here we put in a galvanometer. Okay, so remember, a galvanometer measures well, we might have done before, a galvanometer, that's a symbol for it. It measures small currents. It tells you if there's a current or if there's no current. We'll be using them a lot in electromagnetism, but we won't be doing that until September at this stage. Right, okay, so this is R1, this is R2, this is R3, and this is R4. So the trick in this one is we have to, for it to be balanced, this current must be 0. Okay, so you must rearrange resistance so that current is 0. And if that works, this formula applies. R1 over R2 is equal to R3 over R4. Okay, but only in balance, only when it's balanced. Now the problem with it is that let's say you don't know R4 and you want to find R4. You can find it if you know it. If you get 3 resistors and they just happen to work, so they're balanced, so you have to keep changing the resistors. It could take a long time. Okay, it's a bit of a problem. Okay, so that's kind of a theoretical setup. And in reality, to measure resistance, we use a thing called a meter bridge, which is a version of that. So if I read through this, kind of the way you would expect to draw it, it kind of comes a bit more obvious. Okay, so this, have a pause of this now if you need to, and have a look at it, and satisfy yourself that that circuit is the same as that circuit. This is just the way it's generally drawn. That's the same circuit. And what we're going to do is, if you want to pause and you're satisfied, okay, we're going to replace the resistor R1 and R2 with a length of wire. It's called a meter bridge because that length of resistance wire is going to be 1 meter long. Okay, we'll see it in a minute. Okay, it's 1 meter long, right? And then we're going to go down here and we're going to have a resistor here, which is going to be our unknown resistance. And we're going to have a resistance here, which is going to be our known resistance, which we'll need. We're going to go back to here, okay? And we're going to have a galvanometer down here again. These are effectively resistors R1 and R2, but we don't need R1 and R2. We can say L1 and L2, and there is a sliding contact here called a jockey that you can move up and down, okay? So reality is that R1, the resistance of that wire here, is proportional to L1, and R2 is proportional to L2. And if that's the case, we can say R1 over R2 is equal to L1 over L2. So instead of R1 over R2, we can just say L1 over L2. The ratio is the same. Think about it, it should make sense. Okay, so this formula then becomes L1 over L2 equals R unknown over R known. So if I know resistance, if I move this jockey up and down, and we'll do it in a minute, okay, until the galvanometer reads 0, right, we will be able to write in our L1 and our L2. We will have our unknown resistance, which we don't know. We'll have our known resistance. We'll have 4 variables, 3 of which we know. We can solve using the meter bridge, okay? And it is, the meter bridge is a very nice device because it is what is called a null method, because when you take the reading, there's no current flowing, okay? Because there's no current flowing. When you take the reading, there's no current flowing, which is kind of important because then there's no heating effect on the resistor. Right, so that's it. Okay, so 3 things we've looked at in this class here, okay? Resistance series, we've derived a formula which we'll use tomorrow. Resistance in parallel, we've derived a formula which we'll use tomorrow, and we are interested because it's going to give us unexpected results. And the Wheatstone bridge, with its friend or its version that can be used, called the meter bridge, okay, we have our formula for both of those, not derived, okay, but we're going to, and what we'll do now in a second is we'll see one of those in action in reality, right, and then we are going to look at the 2 experiments, the final experiments, which are very straightforward experiments, okay? We'll do that in a second. Okay, bye-bye.